All right, let's just jump right in. What if I told you that pretty much every single major AI model out there today, we're talking ChatGPT, Gemini, the whole lot, is built on one core idea. And that idea is over a decade old. Yeah. It's an idea that works, it scales, and for the longest time, everyone just kind of assumed that was the only way to do it. Well, it turns out, maybe not. DeepSeek just dropped a research paper that basically challenges that fundamental assumption, and it could totally change how the most powerful AI models are built from now on.
So that old idea, it's called a residual connection. And look, to be clear, it wasn't a bad idea. In fact, it was absolutely revolutionary. Modern AI literally would not exist without it. But, and this is the key part, it came with a hidden trade-off, a limitation that everyone just accepted as, the cost of doing business, the cost of stability. And DeepSeek just found a way to get all that stability without having to pay the price. To really get how they did it, we first need to understand the original problem that this old idea was designed to solve in the first place.
So how do these giant models actually learn? It all comes down to their structure. You've got these large language models, right? They're made of layers, just stacked one on top of the other, hundreds of them. An idea goes into the first layer, it gets processed, passed to the next, and on until you get a final answer at the end. Now, for it to learn from its mistakes during training, the model needs this special signal.
And that signal is called a gradient. You can just think of it as a correction message. It travels backward, all the way from the end to the beginning, telling each layer, hey, tweak yourself a little bit this way. But years ago, researchers totally hit a wall. As they made models deeper and deeper, that gradient signal would either just vanish into nothing, or it would explode into complete chaos. The model just couldn't learn.
And this is where you can really see the scale of the breakthrough. Before residual connections, deep learning was, fragile. Adding more layers could actually make a model worse. It's wild. But residual connections created this stable shortcut, like a clean, open highway for all that information and all those gradients to just flow. I mean, this didn't just improve models, it basically rescued the entire field of deep learning. And its success was so complete that the idea just became part of the furniture. It was infrastructure, something nobody even thought to question.
But here's that subtle trade-off I mentioned. That stable highway for information? Well, it was a single lane. Every little piece of information, every single signal, had to be squeezed through that one narrow residual stream. For years, this was fine, no big deal. But as models got way bigger and started tackling much harder reasoning tasks, this single lane quietly became a serious bottleneck.
So, this bottleneck got researchers thinking, and they asked the next pretty logical question. What if we just widen the highway? Instead of one lane, what if we made a whole bunch of them, letting way more information flow between layers at the same time? And this idea led to a really promising new architecture.
They called it hyperconnections. And on paper, it's a brilliant upgrade. You're giving the model more internal workspace, more ways to combine ideas, more capacity to handle really complex, multi-step thinking. It really seemed like the perfect solution to that bottleneck problem.
And when they actually tried it, the initial results were great. The model started training just fine. The learning metrics were improving, the loss was going down, everything looked perfectly normal. There were absolutely no warning signs of the disaster that was lurking just around the corner. And then, late in the training process, sometimes after thousands and thousands of steps, the entire system would just collapse. The training would abruptly and catastrophically fail. One moment, the model's learning perfectly, and the next, it's complete gibberish. And for large-scale AI, where a single training run costs millions, that kind of unpredictable failure is just not acceptable. So, what was the problem? It really came down to a lack of control. When you have all these multiple streams of information just mixing freely, they start to interact in really unstable ways. Tiny little errors get amplified as they pass from one layer to the next, and then, totally without warning, the gradients just explode. The core idea wasn't wrong, but the execution was just way too chaotic. And that is the exact problem that DeepSeek went after. They developed this new method called Manifold Constrained Hyperconnections, or MHC. Okay, the name is a total mouthful, but the core idea behind it is incredibly elegant. They found a way to get all the benefits of that wider highway, but without any risk of a catastrophic pileup. Okay, so here's the crucial idea. DeepSeek still allows the multiple streams to mix and exchange information, but, and this is the genius part, they constrain that mixing with super strict mathematical rules. So information can be redistributed, it can be blended between all the different streams, but the total signal strength is never amplified or lost. It is mathematically guaranteed to stay constant. And that's really the heart of the breakthrough.
DeepSeek figured out how to get the guaranteed stability of that original single-lane connection while at the same time unlocking the massive extra capacity of a multi-lane highway. It's truly the best of both worlds, with safety baked right into the math itself.
Now, this isn't just some cool idea on a whiteboard. DeepSeek actually built and tested this. They trained models with billions of parameters using their new MHC architecture and put them head-to-head against standard models. And, well, the results really do speak for themselves. Just look at these numbers. The MHC models were consistently better across the board, but the gains were especially huge on tasks that need complex reasoning. On the math benchmark, the score jumped over 7 points. On logical reasoning, another 7-point jump. At this scale, those aren't just small improvements. Those are massive leaps in capability.
So what does that actually mean? Well, by widening that internal pathway from a single stream to multiple constrained streams, DeepSeek effectively increased the model's internal workspace, its capacity to move and process information, by 400%. That is a fundamentally different way of scaling an AI.
Now here's the part that's really wild. It's the efficiency. You'd think a 400% capacity boost would come with a massive cost in training time and hardware, right? But because of DeepSeek's brilliant engineering, they wrote custom GPU code, they optimized memory usage. The total training time only went up by 6.7%, with a hardware overhead of just over 6%. That is an absolutely incredible return on investment.
Okay, so let's zoom out for a second and look at the bigger picture here. This work doesn't just exist in a vacuum. DeepSeek already has this reputation for shaking things up, and this paper really feels like the next chapter in their story.
Think about it. First, their R1 model launch was called a Sputnik moment because it was so efficient. Then their next model got delayed, partly because of chip shortages. And now they publish this paper, openly sharing a technique that is even more efficient. What does that tell you? Well, according to analyst Wei Sun, this is basically DeepSeek signaling to the rest of the world that hardware constraints are not going to stop them. They're innovating at a foundational level, redesigning the very architecture of AI to get more performance out of the hardware they already have. It's a really smart, strategic move to innovate their way around bottlenecks. And that's really the ultimate takeaway here. This manifold constrained hyperconnections thing, it isn't just a cool feature in a new model. It's a potential change to the entire blueprint. It tackles that fundamental trade-off between stability and capacity that has defined AI architecture for over a decade.
Which, it leaves us with a pretty fascinating question. For 10 years, the entire industry just assumed that residual connections were a solved problem. DeepSeek just proved that assumption was wrong. So it really makes you wonder, what other foundational ideas in AI are we all just taking for granted that are actually just waiting for the next big breakthrough?